This is what we have discussed last week. One of the major feature that makes a difference from TCP from UDP is a three-way handshaking mechanism. That's why your TCP headers looks much more complicated than UDP or any other protocols, because their jobs are more complicated. I mean, we start discussing about flow control. All right. Also, I mean, even before anything about flow control, there is a saying hello mechanism. There are different packets that you need to send, you need to exchange between server and client. So 3A handshaking is probably one of the first one that you need to in order to initialize your connections, that this is a typical sequence of packets that you need to exchange. Let me just remind you, 3A handshake, step 1, client host send the TCP SYN, right? What happens, the server receive a TCP SYN packets. So you flip bits of where SYN indicates, and then server recognized as someone try to connect to me by sending a SYN packet. As soon as server receive a SYN packet, they will reply back with the SYN ACK packets. Server host receive a SYN, replies with a SYN ACK segment. Server at the same time, server is getting ready to receive a packet from the client. Things like try to allocate the buffer size, try to allocate certain memory space to start receiving the packets. Try to make a decision on initial sequence numbers. And step 3, when the client received the SYN ACK segment from the server, then it's ready to start exchanging actually the data. So reply with the ACK segment, and then when you first when the client's sending the ACK segment, they can start putting some of the data into that packet. So data are piggybacking to the first ACK packet. After that, it's pretty much straightforward. The sequence that we have discussed, right? This is expected sequence number that I'm expecting from one side. Next ACK is the next expected sequence number. It goes both ways for client and server, right? If it happens between peer-to-peer, then each peer plays both roles for client and server at the same time, right? That was for the initialization. What was the step 4? They try to terminate the connection. What was the packet, the either side, or usually client side? If the client side wanted to terminate the connection, what are their first action to take? Of course, it's not going to be asked on your midterms, but at least for sure for the final exams. So I think they start exchanging the segment like FIN packets in order to tell the servers that I like to terminate the connection with you, and it's pretty much straightforward. As soon as your FIN packet is gone, you're expecting the acknowledgement from the server side. And the server side, after a certain period, the FIN is sent it from the server side this time, and then it's closed after a certain period, timeout. Closing here means you're closing your sockets here for both sides. And this is typical process. However, if termination process are not always happening in this way. I mean, this is one of the nice cases that either end sending a FIN packet. However, if you just disappear from the network, how does the one terminate the TCP connections? No one is sending a FIN packet, right? Yeah, something like timer. It's more appropriate. Assume that you don't receive for packets for a certain period of time. Then you can start assuming that this guy is gone, or you can assuming that this guy's process is maybe closed, suspended, and whatever reasons they are, I don't need to continue for the connections that I had before. So that's typical way of detecting that the other end is disappearing from the network. So how do you, so if that's a situation, if you're asked to continuously keep your connections, what would you do if you're a designer, if you're implementing such applications? And one of the requirements says, do not terminate the TCP connections. And as long as your program's alive, let's keep up with your TCP connections. Timers in the between, so make sure that I send the packet just before closing the sessions automatically. So that way I can continuously have the connection connected. Sessions are connected, right? So they're going to use the certain terms like a semi-permanent connections. I mean, I send the packet once in a while just to make the session alive without going through all this, right? So there are many applications that continue to try to keep it that way for whatever reasons they have. So I just try to give you example for the cases that this fin not happening, and also cases for that you like to keep alive. You like to keep your sessions alive all the time. Maybe sending packets once in a while, just to make sure that you have the other end, the sockets are opening. However, whatever I do, I mean, in terms of TCP, we need a three-way handshaking mechanism for when we are initializing the connections. Without that step, we don't have a TCP connections. Okay? So those are the typical, pretty much one of the most differences of a TCP from UDP port. So I think that's what we discussed mostly last week. I mean, before that, we discussed about pipelining, and we'd like to make sure that your receiver side buffers doesn't overflow by negotiating what? What was the mechanism to make sure that your receiving side have enough space to receive a packet? Right, so what do you have to tell the sending side from a receiver side? 뭘 보내야 돼? What was the way to managing that speed? Sending ratio, for example. Window size, right? They give you simply example on how to compute a window size. Simply means how many packets can you put it onto a pipe without a ACK packets, right? So you're negotiating the size. By negotiating means here you're also negotiating your sending and receiving ratio of the data itself. So that's pretty much what we have discussed last week, I hope. 맞죠? And then I think we start moving into the congestion control. We start looking at the first setup slide, and I think we ran out of time to stop it. Well, principle of congestion control is flow control covered, connection management, three-way handshaking, how to terminate your connections are discussed. Principle of congestion control, I told you already in terms of general concept, flow control is just between two ends, server and client side. Make sure either one of them having a not too much. This congestion here means for the network congestions. If your network in the middle having too much of packets, that will be also loss or delays maybe happening in the between part. How do we make sure that your network in the between doesn't overflow, for example? One of the ideas that you can try if you're designing the protocol like this, if there is someone in the middle, if you can ask network, are you busy? Then it would be nice, right? It would be nice. Then network says, I'm busy, so I send it less. However, that's not the case. There is no one to ask for those type of specific questions. Well, in terms of flow control, there is someone to ask, right? We could ask the receiver side, what is your full buffer size, for example? So idea is somewhat distributed. you give a freedom for every node participating in the network and try to sacrifice little bit by little bit, so everyone wanted, at the end, everyone wanted to have a fair share of the network resources. Bandwidth, for example. Right? That's the main idea for this. Informally, too many sources are sending too much data too fast for a network to handle. Old-fashioned network, old Ethernet fashion. There is a way to handle this problem. However, we're discussing in the transport layer here and more recent technologies. What is a possible consequences of these network having too much packet, lost packets, delay, long delays, right? Delay components that we have looked at. Basically, the queues in the between, having those queues holding holding packets just too long. So delivery time from one end to the other is increasing more and more. So here are the causes and cost of congestion for first scenario. So there is something in the middle. Of course, this is network. Network consists of the routers or switches in the middle, right? But we all know that by now these router switches are nothing more than a queue, right? Having a queue, receiving packets, and they're waiting to be forwarded to some other routers in the between, right? Two senders, host A and B, your PC, whatever, your smartphones, and there are two receivers. Well, in this case, you can think of servers, I don't care. Two different servers. There is one router, infinite buffers. So there is no restriction of the buffers. So as many as I can send, there will be less things to worry about for me about buffer size overflow. So there's going to be a node retransmission. And assuming that there is going to be a node retransmission in this case. So this is meaning for in means the data that I'm sending it out. Here, receiving data coming in from outside to this guy. So how much I send, how much the receiver receives. So if I draw that in this figure like this is inside, outside. C representing the total capacity of the link in the between. And there's two servers. So at some point, simply that graph says maximum speed that I can have for this scenario for a single host is just half of its capacity of the link. So they're sharing the link nicely. 50% of the speed is going to this guy, 50% of speed is going to this guy. Well, theoretically, you cannot gain more than half. I mean, no one is getting more than the others, right? Delays, delay will increase when? I mean, the time that stay within this queue will increase when? When the queue is keep filling up. However, we have an infinite queue size. So longer time that we spend, it means that whenever we are reaching up to the maximum speed that we can allow theoretically, the delay will increase dramatically here. So delay of this inside, the sending it from sender side to the receiver side. When it's close to the half of its capacity, delay will increase substantially. Right? If you think about it, that's a natural thing happening. What about other scenarios? Like this time, scenario 2, one router, finite buffers. So buffer has a limits now. If we start having a buffer with the limits, then there might be cases that some of the packets cannot get into the buffer space, cannot get into a queue. So that packet may get lost somewhere in the between. Because there is no space for certain packets to go into the router. Network doesn't know what to do, maybe they just simply ignore it. Sender retransmit the timeout packets. Application layer inputs, application layer outputs are equal for both sides. So in terms of application layer point of view, what I'm sending, the message size, is the same as what I have. What receiver receives to the application layer message will be equal to the whatever the sender sent from the application layer. However, there is a chance for retransmission if this buffer is full. So then it means that there is a chance that I might be sending a bit more than what the message was, bigger than what the original message size from the application layer, if you think about it, right? When we're discussing for the RDT 3.0, RDT 2.0, I mean, there is always step for if your packet didn't get there, if you didn't receive an ACK or whatever the timeout happening, they say send it again, right? So, but your message size from the application layer is maybe 100 bytes. There is a chance that you, from the transport layer, IP layers, you might be sending 120 megabytes. Those 20 megabytes is due to the retransmission of the packet that didn't get there. So obviously, what I've sent could be bigger than what the original, what the application layer size messages are. So it's quite natural things to see. 그치? 뭐 너무 당연한 얘기죠, 그죠? 어플리케이션 레이어에서 100메가 보내는데 어플리케이션은 100메가 보냈으면 저쪽 어플리케이션에서 100메가를 받는 거고, 근데 트랜스포트 레이어를 보면 중간에 리트랜스미션 보내고 하게 되면 100메가보다는 더 보낼 수도 있는 거죠. 그죠? 너무 당연한 얘기죠. So original data plus retransmission data. So it's bigger. What could be the good case is ideal case is a sender sends only when the router buffer is available. Then it'll be nicer. Then we can reach something like this. If this is happening, the ratio R also ratio of the capacity of the link. Well, we just, whatever I send, when it reaches the half of its capacity, everyone's happy, just half of it. So 2 senders, 2 receivers. Only if the routers can tell me, they can tell the node that there is enough space in my buffer, so you can send it now. That's a very ideal cases. And then I'll have a graph like that. But that's not the actual network like, right? That's not the actual network like. So total ratio between these two, one server and one client, one sender and one receiver, is slightly deviated. This graph will be slightly deviated. Maybe I need to send a bit more, assuming there's going to be a losses happening. So this is more realistic. And because we don't have a infinite buffers, we do have a finite buffers, and there could be a loss happening, whatever reasons in the between. Packets may get dropped at the router due to a full buffer. So queue full, packet coming in, but there is no space in the router's memory, dropped. Just disappear. That bit's gone. And I can do that because these channels are unreliable. I can do that. I have a faith in the TCP, then they will send it again. They will try it again. Hopefully next try, when they send it again, this queue has some spots left. That packet can get into this queue, right? Actually, routers have those algorithms, such an algorithm for that part too, like early drop algorithm, like red. Things like the idea is like router, from time to time, they make a prediction on, I need to clear up my queue because there to be a coming packets. Make sure I don't have any losses. So they intentionally maybe make it drop from the buffers. So sometimes a lost sender only resends the packets known to be lost. So obviously, what I'm going to sending here, again, it's going to be slightly more than what's from the application layer message size. Then the graph will be deviated a little bit from those nice linear graph to just drop because there is no space in the queue. Obviously, your graph, in order to get to the half of its ratio, I mean, we're still sharing by the 2. But obviously, I need to send a bit more. That's why the graph looks to be longer on this side until I reach the half of its capacity. So we use that C, we can use on our ratio or capacity, doesn't really matter, it's the same thing. So graph is pretty much straightforward. So more data I need to send from the TCP side, transport layer side, so I can reach up to the fastest maximum ratio of a one host to the one receiver side in this particular scenario. So anyway, I mean, so I know. I'm gonna repeat some of this slide next week, but just stay with me. I mean, the graph makes sense, right? 이건 말이 되잖아. We like to get well, that's a theoretical bound. I like to share this link speed half and half. And obviously, I need to send a bit more than what original data has sent. So this is a time that takes more data that I need to send. Then I will get to the point where I have a half of its link capacity ratio, sending ratio. So when sending rate of by half, some packets are retransmitted, but good asymptotic good put is still the R divided by 2. R's half of its capacity. 뭐 당연히죠. It's a maximum that I can get to, maximum ratio that I can get to. Same thing for the duplicate, same examples. Sender times out prematurely sending 2 copies, both which are delivered, same things. Maybe timeout happened while still in the queue, and the early timeout happened. They're gonna send it again before they receive an ACK or something. So, likewise, that's an unnecessary retransmission, things that I need to send it more. Why do I want to waste the network resources? I mean, if I don't send that packets, that data portion could be used by someone else. I could use that data for transmitting the next set of bits, right? The whole idea is we like to be fair and we like to minimize any waste in the network. So I like to have nice utilization, for example. So same thing again, some packet retransmissions due to duplicates, you still need to send more than is necessary. So this is a waste. Cost of congestions. More works, more retransmissions for given good put. Unneeded retransmissions, link carries multiple copies of packets, decreasing good puts. There is a ratio that I can get to. However, due to these retransmission packets, many of them are unnecessary. I cannot get to the speed that I wanted to get to. I mean, theoretical bound. So we like to minimize. And this is only 2 host cases. We start jumping in many different hosts. How can we achieve this? And actually, the main idea is we're giving a responsibility to the host only this time. So host, your TCP will have to figure out how much they can send by a very simple trial and error. Idea is very simple. I send my packets 1, 2, 3, 4, 5 until up to the point that I feel that I don't deliver my packets okay. Then I reduce my speed Imagine that every node participating in network are doing so. Then eventually for the long-term observation, everyone will be reaching to the certain point. And hopefully that point is a fair point for everyone in the network. So, in terms of retransmission, if we collect the packets from the mobile network, for example, your 3G, LTE packets, surprisingly many retransmission packets will be happening. Nowadays, the data, I don't know how much you guys pay per month, but usually, I don't know, $20 to $30 per month. Is it? For how much of the data? You guys don't pay anything for the 3G LTE? I'm sure. I don't know. If you pay $20 per month in this country, you can get a data plans for 300 megabytes free per month. Or if you pay a bit more, then you can get a data plans like 750 megabytes free of the data, right? Or if you pay more, then you can get 2-3 gigabytes per month free, right? They say it's free, but you already paid for the part. Imagine that half of those traffic is retransmission. You're wasting your money for those data that you did not use. Your TCP used it for your reliable data transfer for that part. Right? You pay $30 for 1 gigabytes of data free, but what you are actually using is 500 megabytes. That sounds really unfair. Right? That sounds really unfair. Nowadays it's better, but before this data charging, we used to charge by the packets. Right? I'm sure you guys have used similar plan when you guys in high school or similar. Just a few years ago, maybe 3 to 4 years ago, all the data plan was charged by packets. So 10 cents per packets. Right. That is the usually data plan. Imagine that you be paying extra money for retransmission packets. That's really unfair, right? But that was actually what's happening before. So whether you know it or not, lots of money was wasted. Your pocket money was wasted on these retransmission packets when the network was unreliable and not stable enough. So government actually wanted to do something about it. And LTE, I'm not so sure about LTE's retransmission ratio. It's supposed to be less than 3G or HDSP with the older data technologies, but still I believe there is some portion of the data are still retransmission. It used to be up to 40 or more % of the packets are retransmission. So you're just paying half. You're just using what you have. You're just using half of what you have paid. Hopefully LTE is less than 20 or 10%. 말이 안 되지? 근데 실제로 그렇게 했었어요. 그러니까 네트워크 회사들은 꽁돈 번 거죠. 그렇죠? 꽁돈을 벌었다 보면 걔네 입장에서도 패킷이 그렇게 되는데 뭐 어차피 그 패킷은 자기 네트워크로 왔다 갔다 하는 거니까. 옛날에는 다 패킷으로 했잖아. 지금도 when you go outside the country, if you're roaming your service, they actually charge by packets, right? 1 cent per packets. 그렇죠? If you try to do that outside and you try to access certain servers back in home, then you will experience lots of retransmission. So you're paying a lot more than what you do. You're paying actually less value. Well, it's pretty much what I have said. What I wanted to get to is this is what's actually happening. Because the congestion happening after a certain point, doesn't matter how much that I'm sending, the receiver will having a difficulty receiving the packets. This is a receiver side arriving ratio. This is the sending side sending ratio. Up to a certain point, everyone is happy. What I have sent, they received. However, there are more sending coming into the network, and your network getting busy. Your speed is decreased rapidly. At this point, no one is happy. You just keep sending more, everything is wasted because of the buffer size, because of the delays happening. This is a general description of the congestion that we will be experiencing. Simply imagine that we have a 40 something, close to 50 students in this room, like to connect to the same Wi-Fi at the same time. Everyone try to run a BitTorrent at the same time. Try to download something. Initially, for first 10 seconds, everyone seems to be getting some data. After maybe 10, 20 seconds, no one is getting any data. But they're still getting the data with a very small ratio of the size. Congestions. We congested the network in the between. Another cost of the congestions. When packet dropped, any upstream retransmission capacity used for that packets were wasted. Doesn't matter how much I send, it's going to be wasted. A lot of retransmission dominating. No one is happy. No receiver is happy of what they're getting. That's exactly what's happening for the congestion. And that's why we need to consider for the congestion control part from each end. Approaches toward the congestion control. Again, simple idea. You can ask. If you can ask someone in the middle, that's probably the best, right? It's nicer. However, there could be some capacity problem too, right? So let's take a look. Two broad approaches toward the congestion controls in terms of concept. End-to-end congestion control. No explicit feedback from the network. There is no one to ask. There's no one to ask. End-to-end. Logical layer. Logical network. Assuming there's, well, when we draw the logical network, right? We don't care what's in the between like this. We don't draw a router, we don't draw nothing, right? Only sender and receiver are being considered for end-to-end, right? So no one here to ask. No explicit feedback from network. Congestion inferred from the end system's observation of loss, delays. So I'm going to just rely on from my system. Well, if I'm sending a packet, I can measure my own RTT, right? I can measure my own RTT, right? We discussed about measuring RTT, use that value to make the right timeout values and etc., right? What was it again? How do you compute? What was the suggested way of computing timeout values for measured RTT? 뭐였어? I should have included that into the midterm coverage. Estimated RTT plus 4 times standard deviation of RTTs, right? Something like that. Predicted RTT, weighted value, exponential weight values in the between. End systems can figure out its, should be, inferring means here is try to guess what's going on in the network because there is no one to ask in the between. So maybe I can guess from the data that I can compute. RTT is one of the good ones, right? How much time does it take to get the messages back, right? Delays can be estimated, right? Trace route, we did take a look at the trace route, right? Maybe based on the data we can guess. Maybe my delay gets larger, assuming that network having a congestion problems. So things left, maybe my option is to maybe reducing number of packets that I can send, maybe. This is approach taken by TCP. TCP will try to figure its own without asking anybody in the between, which makes sense. Another way, you can ask the network. You can ask the switches and routers for current situations. It's different protocols are being used in this. Usually for bigger network, the core network. It's not happening in the Ethernet. Network-assisted congestion control. So network are aware of there are certain situations. Routers provide the feedback to the end system. If end system requested or without request, routers will tell the host that I'm having a difficulty of congestion, so try to reduce your sending ratio, for example. Single bit indicating congestion. These type of stuff or protocols are being used for many different protocols. Slightly different type of TCP/IP or DAC bits or ATM. It's usually used for a core network. It's not the same ATM. It's not the same ATM machine that we use. It's not a cash drawing machines. 그죠? 그 중간에 백본에 큰 트렁크 할 때 ATM망을 쓰기도 해요. 많이 써요. 백본 쪽에. 그런 애들은 backbone network, they actually can ask. Huh? Backbone, it's a bigger network in the middle. Bigger network in the middle. backbone이란 말이 익숙치 않겠구나. I think we will discuss what's a backbone network. I think the first few chapters, somewhere in there, they try to give you idea for what's a backbone network, but we're usually referring to the core network in the middle, and backbone will be discussed again when we start discussing about routers, routing protocols, and etc. Explicitly rate senders should be sent at, so they can actually tell how much ratio they should be sending. So two approaches: ABR, available bit ratio, elastic services. If sender's path is underloaded, means that there is lots of space in the trunk that I can send, so send it more. Yeah. Sender should be using the available bandwidth. Easily put, if you try to watch the same YouTube video clip from your mobile network or from your PC that is connected to your landline, YouTube usually adjusts their sending ratio, right? If you're using a poor connection of a 3G mobile, YouTube video, movie video is usually very poor quality. It means the data size are lower than the typical quality. If you're using a nice connections, they actually send you the rates of quite high ratio, so you can watch a high resolution video clips. ABR is a similar idea for that part. 그지? 유튜브 보다 보면 핸드폰에서 볼 때랑 PC에서 실제로 선 꼽아져 있을 때 볼 때랑 핸드폰에서 볼 때는 가끔씩 그 퀄리티가 좀 낮은 거로 오죠. 그죠? 그럴 때 네트워크가 상황이 안 좋으면 좀 줄여서 보내주고, 네트워크가 좋으면 좋은 하이 퀄리티로 보내주고. 그죠? Very similar idea for the ABR. That's what it means to have elastic services. Things can be changing more dynamic ways. If senders' paths are congested, sender throttles to minimum guaranteed rate. So they reduce their sending ratio, perhaps until the limit of this is the minimum limit that I need to have, maybe minimum quality of service ratio. So it simply means I reduce the sending ratio if I detected something. RM, resource management cells, sent by sender, interspersed within the cell, bits in the RM cell set by switches. It's this approach for this, and then this approach is for network assisted ones. Okay, there is something in the middle that can tell about network congestions with a single bit. Okay, so you don't need to know the exact bits. It's all different, but you can use a NI bits like no increase in the ratio, mild congestion. So you tell by sending a small message containing these two bits that if NI bit is flipped, it says 1, then sender receives that data. Look at NI bit is on, then they do not increase their sending ratio. They keep up with their current sending ratio. If the CI bits, congestion indicating bits, are flipped, it says 1, then host, maybe they can reduce their sending ratio. So something in the middle, resource managers, RM things are actually telling the host what to do in very simple ways, only 2 bits maybe, for example. RM cells are returned to sender by receiver with the bit intact. What we are more interested in is for TCP behavior, end-to-end congestion control. That's more familiar with us. We don't care too much about what's in the middle part yet. So, TCP congestion control. Again, end-to-end congestion ways, assuming I have no idea in the middle part, no idea what's going on in the middle. I think if you do bonus questions for them, the assignment 2, you probably already have solved these questions. And I'm guessing no one did the bonuses yet. So it's running out of time. So it's okay. I'm going to give you a solution to the bonus questions in the next set of assignment anyways. So if you didn't do it for your bonus questions for this time, please do that for the next set of assignment. Okay? With both. TCP congestion control, something called additive increase, multiplicative decrease. Additive increase and multiplicative decrease. That actually 4 words describe everything about this TCP congestion controls. But I already give you the idea. Send, if I'm sending too much, decrease. Send again, too much, decrease. They actually give you the ways of how to increase and how to decrease. If you actually take a look at it, it's a quite dumb way to do it. But it's actually still working fine ways of doing so. Approaches, increase the transmission ratio. Again, transmission ratio, in order to increase my transmission ratio at TCP/N, only options that I have is window size. Increase my window size. Send more packets within the same window scale. Proving for usable bandwidth until loss occurs. Proving usable bandwidth simply means that proving is a common term to use it. If I like to know how much bandwidth that I can use or what's RTT that I have, I send 1 packet and see. That particular act of sending a sample packet and to measure what's going on is something called proving part. We also used it for the occasions that when you wanted to discover a certain host in the network, you send the proving packets, see what kind of host you can get it from. Let me just quickly finish this slide and next few slides regarding this graph, and then I will give you some time to study for your midterm for 10 minutes, and then you can. So stay with me for a few more minutes. Additive increase. Increase the current window size by 1, maximum segment size. So just think of it as window size plus 1. Increase my window size by 1. So every RTT until loss is detected. Every time I send 1 packet, I compute for RTT based on the ACK that I receive. And until there is no loss happening, I'm gonna increase my windows size by 1. Start from, I don't know, I start from 4, 5, 6, 7, until my RTT says something is not right. So, multiplicative decrease. When that happens, if the host figure out there's something happening, the loss happening, or loss happening, how do you know the loss happening in my side? 어떻게 알 수 있어? Yeah, timeout happening, for example. So, cut the window size by half. So I go like 4, 5, 6, 7, 8, 9. 연애한다 저기. 4, 5, 6, 7, 8, 9, and then, for example, timeout happening, or loss seems to be happening. I cut down my window size by, it was 9 by half, maybe 4. I drop it by half. So I'm being very cautious. I don't want to give too much packets into the network. So I'm cautiously increasing my window size. When something happens, I decrease my window size by half. So backward, moving back more cautiously. Something called sawtooth behavior. So if you count that, if you're drawing that behavior onto this plane, time goes this way. If this left side is keeping track of your window size, it's going to be like this. Up, down, up, down, up, down, up, down, up, down, like this. And this is something called sawtooth behavior. sawtooth가 뭐야? 상어 이빨. It's a very sharp behavior. So, proving for the bandwidth. So imagine that I don't experiencing any losses. Imagine that there is only one host, one receiver in the network. Network is huge enough. It means that I'm never going to experience a losses for a while. That my window size keep growing. Isn't that what's happening? If no one is using the current internet now in the Wi-Fi, you are the only one who is using the internet. You will get the best speed out of it, right? And if someone start jumping into the network, then you need to back up a little bit. So you're giving up your spaces for someone else in the network. What's happening is you cut down your window size. So in a way, it's a very smart move. You're giving no one in the middle controls that, but in this way, they can adjust their sending ratio by automatically. I mean, without talking to each other. Somewhat distributed ways. So it's I know it's seems to be a dumb approach, but it's a quite effective approach to do it. Otherwise, I don't know how to do it. Otherwise, you have to come up with the protocol messages that you're talking to everyone in the network. But that's not feasible. That's not practical enough. Right? We did discuss about computing the current window size, right? I mean, last byte send the byte that you want to do it. And if you just divide by the RTT, bits per second by the byte size, then that gives you the ratio. Anyways, you can compute that quite easily, byte per second. So current window size is dynamic functions of the perceived network congestions. Perceived here, loss of packets, or any time that things like timeout happen or duplicate packets, duplicate ACK arrives, right? Those are the typical signs for something is not right. Oh, 여기 있네. How does the sender perceive how to detect the congestions? Loss of event, timeout, or 3 duplicate ACKs. A TCP sender reduces the ratio after loss events. 3 mechanisms: additive increase, multiplicative decrease, slow start, conservative after timeout event. You're being careful about after loss happening because you don't know exactly what's happening. So we're going to take a look at the slow start first. This is what you guys experience every single day, but you never use the term to slow start to cover it. I mean, once you connected to a certain service, initially your speed, BitTorrent, just think of BitTorrent, it's a great example. But BitTorrent have a slightly different issue than TCP. Or any downloading service. You can see that your initial download speed increased. This is time from your device downloading speed, maybe in bits per second. But start downloading, you can see that your speed increasing initially, and then it seems to be stay like this. This is typical behavior, right? We try to look at this part, where we try to increase our speed up to the levels that I'm okay. Maybe this is the point that I don't experience too much of loss. To be more exact, according to the sawtooth path, it's actually what's happening like this. So the first part is TCP slow start. When the connection, I'm just going to read it. When connection begins, increase the rate exponentially until first loss event. Initially, current window size is 1. Double window size every RTT. Exponential growth now. 2, 4, 8, 16, 32. Right? Done by incrementing current window for every ACK received. Summary, initial rate slow, but ramps up the exponentially fast. So if I draw that exponentially fast, maybe it might be more useful like drawing like this. And then maybe.